is not statistically significant. And this is confirmed by the large p-value, the area under the standard normal curve that is further than 1.47.
I'm so over this house.
I'm so into this house.
It's been completely untouched.
Completely untouched for 100 years.
StatQuest is on my mind all night long. StatQuest. Hello, I'm Josh Starmer and welcome to StatQuest. Today we're going to talk about odds ratios and log odds ratios, and they're going to be clearly explained. The StatQuest on odds and the log of the odds ended in a cliffhanger. We talked about how the odds are just the ratio of something happening, i.e. my team winning, to something not happening, i.e. my team not winning. We illustrated this with circles. Blue circles represented my team winning. Red circles represented my team losing. And the odds of my team winning were just the blue circles over the red circles. Alternatively, we could just use numbers to represent the odds. And when we do the math, we see the odds of winning are 0.5. The cliffhanger came when I said that even though the odds are a ratio, it's not what people mean when they say odds ratio. So let's clear this up once and for all. When people say odds ratio, they're talking about a ratio of odds. So we've got a ratio of these odds to these odds. Doing the math gives us 2 divided by 4 over 3 divided by 1. And that gives us 0.17. Just like when we calculate the odds of something, if the denominator is larger than the numerator, the odds ratio will go from 0 to 1. And if the numerator is larger than the denominator, then the odds ratio will go from 1 to infinity and beyond. And just like the odds, taking the log of the odds ratio makes things nice and symmetrical. For example, if the odds ratio is 2 divided by 4 over 3 divided by 1, then the log of the odds ratio equals negative 1.79. And if the odds ratio is the opposite, it's 3 to 1 over 2 to 4, then the log of the odds ratio is the positive version. It equals 1.79. Great! Now that we've got that cleared up, what can we do with odds ratios? Here's an example of the odds ratio in action. We've got a bunch of people, 356 to be exact. 29 of these people have cancer, and 327 do not. We also know that 140 of these people have the mutated gene. I'm just going to let you imagine which gene I'm talking about here. And 216 people do not have the mutated gene. We can use an odds ratio to determine if there's a relationship between the mutated gene and cancer. If someone has the mutated gene, are the odds higher that they will get cancer? Given that a person has the mutated gene, the odds that they have cancer are 23 to 117. So we'll put that on top of the odds ratio. And given that a person does not have the mutated gene, the odds that they have cancer are 6 to 210. So we'll put that on the bottom of the odds ratio. Here's our odds ratio. We do the math, and the odds ratio tells us that the odds are 6.88 times greater that someone with the mutated gene will also have cancer. And the log of the odds ratio is 1.93. Small bam. What does all this mean? The odds ratio and the log of the odds ratio are like r squared. They indicate a relationship between two things. In this case, a relationship between the mutated gene and cancer. And just like r squared, the values correspond to effect size. Larger values mean the mutated gene is a good predictor of cancer. Smaller values mean that the mutated gene is not a good predictor of cancer. Bam! However, just like r squared, we need to know if this relationship is statistically significant. So let's do it. There are three ways to determine if an odds ratio, or log of an odds ratio, is statistically significant. 1. Fisher's exact test. 2. A chi-square test. And 3. The Wold Test. One super annoying thing is that there is no general consensus on which method is best, and people often mix and match. General consensus test. Wold test. One super annoying thing is that there is no general consensus on which method is best, and people often mix and match. Some people will use Fisher's exact test or the chi-square test to calculate a p-value, and use the Wold test to calculate a confidence interval. And some people are happy to let Wold do all the work, calculate the p-value and the confidence interval. The last method ensures that the p-value and confidence interval will always be consistent, but check and see what other folks do in your field to find out what is most acceptable. So let's start with Fisher's exact test. Step 1. Watch the StatQuest on enrichment analysis using Fisher's exact test and the hypergeometric distribution. Bam! Now think of the people as a bag of tasty M&Ms. People with cancer are represented by 23 plus 6 equals 29 red M&Ms. People without cancer are represented by 117 plus 210 equals 327 blue M&Ms. Now, just like in that StatQuest, we work out the p-value for grabbing a handful of 23 red M&Ms and 117 blue M&Ms. And just like in that StatQuest, we use a computer and it says the p-value equals 0.00001. Another small bam. Now let's talk about how to calculate the p-value using a chi-square test. The chi-square test compares the observed values to expected values that assume there is no relationship between the mutated gene and cancer. To do this, we calculate the probability of having cancer as the total number of people with cancer. That's 29. Divided by the total number of people. That's 356. So the probability of having cancer is 0.08. So if the gene is not associated with the 23 plus 117 equals 140 people with the mutated gene, then the probability of having cancer times the number of people with the mutated gene equals 11.2. Thus, the expected number of people with the mutated gene and cancer is 11.2. And the remaining 128.8 people with the mutated gene are expected not to have cancer. Likewise, if the gene is not associated with the 6 plus 210 equals 216 people without the mutated gene, then the probability of having cancer times the number of people without the mutated gene equals 17.3. Thus, The expected number of people with cancer that do not have the mutated gene is 17.3. And the remaining 198.7 people with the mutated gene are expected not to have cancer. Now we do a chi-square test to compare the observed and expected values. And the p-value is 0.00001 with the continuity correction and 0.000004 without the continuity correction. If you're not familiar with the chi-square test, don't panic. We'll do a StatQuest on it. One last small bam. Lastly, let's talk about the Wold Test. This test is commonly used to determine the significance of odds ratios in logistic regression and to calculate confidence intervals. The Wold Test takes advantage of the fact that the log of the odds ratios, just like the log of the odds, are normally distributed. This is a histogram of 10,000 randomly generated log of the odds ratios that tells us what to expect if there is no relationship between the mutated gene and cancer. Psst! If you want to draw this histogram at home, randomly pick a total number of people between 300 and 400. We do this to simulate the fact that if we repeated this experiment, we might not get the exact same sample size each time. Then, for each sample, select a random number between 0 and 1. If the number was less than 0.08, the proportion of people with cancer, then the sample has cancer. Then, pick another random number between 0 and 1. If the number was less than 0.39, the proportion of people with the mutated gene, then it has the mutated gene. This gives you a matrix of random values that did not depend on a relationship between the mutated gene and cancer. Lastly, calculate the log of the odds ratio. Do this 10,000 times and draw a histogram. A normal curve fits pretty well. Notice that the histogram and curve are centered on 0. When there is no difference in the odds, the log of the odds ratio equals 0. The standard deviation of the 10,000 log of the odds ratios is 0.43. However, it is more common to estimate the standard deviation from the observed values. If a mutated gene, then it has point if for histogram at home and cancer. Psst! If you want to draw this histogram at home, randomly pick a total number of people repeated. Then, for each sample, select a random number between 0 and 1. Cancer, then the at home, randomly to size each 0 and 1 portion, then less than 0.39, the proportion of people with the mutated gene, then it has the mutated gene. This gives you a matrix of random values that did not depend on a relationship between the mutated gene and cancer. Lastly, calculate the log of the odds ratio. Do this 10,000 times and draw a histogram. A normal curve fits pretty well. Notice that the histogram and curve are centered on 0. When there is no difference in the odds, the log of the odds ratio equals 0. The standard deviation of the 10,000 log of the odds ratios is 0.43. However, it is more common to estimate the standard deviation from the observed values. You do this by taking the square root of the sum of 1 over each of the observed values. If we do the math, we get 0.47. The two different standard deviations that we calculated are very similar. All that the Wold Test does is look to see how many standard deviations the observed log of the odds ratio is from 0. And since the Wold Test typically uses the estimated standard deviation, We'll replace the histogram with a normal curve centered on 0 that has a standard deviation of 0.47. The log of the odds ratio is the same one that we already calculated. Here's where the log of the odds ratio goes on the curve. To find out how many standard deviations the log of the odds ratio is away from 0, we simply divide by the standard deviation. Thus, we divide 1.93 by 0.47. And that gives us 4.11. So our log of the odds ratio is 4.11 standard deviations away from the mean of the distribution. A general rule of thumb with normal distributions is that anything further than 2 standard deviations from the mean will have a p-value less than 0.05, so we know our log of the odds ratio is statistically significant. However, to get a precise two-sided p-value, we can add up the areas under the curve for points greater than 1.93 and for points less than negative 1.9. The areas under is the 5. Random value not having a standard deviations away from 0. The second coefficient is the slope. It means that for every 1 unit of weight gained, the log of the odds of obesity increases by 1.825. Here's the standard error for the slope. Again, the z-value is the number of standard deviations the estimate is from 0 on the standard normal curve. And again, the estimate is less than 2 standard deviations from 0, so it is not statistically significant. This is no surprise with such a small sample size. And this is confirmed with the large p-value. Double bam! Now we know all about the logistic regression coefficients when we use a continuous variable like weight to predict obesity. Now let's talk about logistic regression coefficients in the context of testing if a discrete variable like whether or not a mouse has a mutated gene is related to obesity. On the left side, we have mice that have a normal gene. And on the right side, we have mice with a mutated gene. Just like before, some of the mice are obese, and some of the mice are not obese. This type of logistic regression is very similar to how a t-test is done using linear models. So let's do a quick review of how a t-test is done using linear models. Shameless self-promotion. If you're not already familiar with how a t-test can be performed using a linear model, then check out the StatQuest, Linear Models Part 2, T-Tests and ANOVA. Okay, we start with some data. In this case, we've measured the size of mice that have a normal gene, and the size of mice with a mutated version of that gene. Then we fit 2 lines to the data. The first line represents the mean size for the mice with the normal copy of the gene. The second line represents the mean size of the mice with the mutated copy of the gene. These 2 lines come together to form the coefficients in this equation. The mean value for size for the mice with the normal copy of the gene goes here. And the difference between the mean size of the mice with the mutated gene and the mean size of the mice with the normal gene goes here. We then pair this equation with a design matrix to predict the size of a mouse given that it has the normal or mutated version of the gene. This is the design matrix for the observed data. The first column corresponds to values for B1, and it turns on the first coefficient, the mean of the normal mice. The second column corresponds to values for B2 and turns the second coefficient, the mean of the mutant mice minus the mean of the normal mice, off or on, depending on whether it is a 0 or a 1. For example, the first row in the design matrix corresponds to a mouse with a normal copy of the gene. We predict its size by replacing B1 with 1 and replacing B2 with 0. And then we just do the math. And we see that this mouse is associated with the mean of the normal mice. The mice and use it to calculate the log of the odds of obesity. Another that all those fancy things we can do with linear models, like multiple regression and ANOVA, odds.
Hi! In every competition, we need to pre-process given dataset and generate new features from existing ones. This is often required to stay on the same track with other competitors, and sometimes careful feature pre-processing and feature engineering can give you the edge you are striving to achieve. Thus, in the next videos, we will cover a very useful topic of basic feature pre-processing and basic feature generation for different types of features. Namely, we will go through numeric features, categorical features, datetime features, and coordinate features. And in the last video, we will discuss missing values. Besides that, we often will discuss dependence of pre-processing and generation on the model we are going to use. So, the broad goal of the next videos is to help you acquire these highly required skills. To get an idea of following topics, let's start with an example of data similar to what we may encounter in competition, and take a look at a well-known Titanic dataset. It stores data about people who were on the Titanic liner during its last trip. Here we have a typical data frame we work with in competitions. Each row represents a person, and each column is a feature. We have different kinds of features here. For example, the values in survived column are either 0 or 1. The feature is binary, and by the way, it is what we need to predict in this task. It is our target. So age and fare are numeric features, CBSP and parch are counts, sex, cabin and embarked are categorical features, ticket is just an ID, and name is text. So indeed, we have different feature types here, but do we understand why we should care about different features having different types? Well, there are two main reasons for it, namely, strong connection between pre-processing and our model, and common feature generation methods for each feature type. First, let's discuss feature pre-processing. Most of times, we can just take raw features, fit our favorite model, and expect it to get great results. Each type of feature has its own ways to be pre-processed in order to improve quality of a model. In other words, choice of pre-processing method depends on the model we are going to use. For example, let's suppose that target has non-linear dependency on p-class feature. P-class value of 1 usually leads to target of 1, 2 leads to 0, and 3 leads to 1 again. Clearly, because this is not a linear dependency, linear model won't get a good result here. So in order to improve a linear model's quality, we may want to pre-process p-class feature in some way, for example with a so-called one-hot encoder, which will replace our feature with 3, 1 for each of p-class values. The linear model will fit much better now than in the previous case. However, random forest does not require this feature to be transformed at all. Random forest can easily put each p-class in separate leaf and predict fine probabilities. So that was an example of pre-processing. The second reason why we should be aware of different feature types is to ease generation of new features. Feature types differ in this, and comprehending common feature generation methods will gain you an ability to improve your model through them. Also, understanding of basics of feature generation will aid you greatly in upcoming advanced feature topics from our course. As in the first point, understanding of a model here can help us to create useful features. Let me show you an example. Say, we are to predict a number of apples a shop will sell each day next week, and we already have a couple of months' sales history as a training data. Let's consider that we have an obvious linear trend throughout the data, and we want to inform the model about it. To provide you a visual example, We put here the second table with last days from train and first days from test. One way to help model utilize linear trend is to add feature indicating the week number passed. With this feature, linear model can successfully find an existing linear dependency. On the other hand, a gradient boosting decision tree will use this feature to calculate something like mean target value for each week. Here, I calculated mean values manually and printing them in the data frame. We are going to predict number of apples for the 6th week. Note that we indeed have linear trend here. So let's plot how gradient boosting decision tree will split the week feature. As we do not train gradient boosting decision tree on the 6th week, it will not put splits between the 5th and the 6th weeks. Then, when we will predict number of apples for the 6th week, the model will end up using the value from the 5th week. As we can see, unfortunately, no usage of linear trend here. And vice versa, we can come up with an example of generated feature that will be beneficial for gradient boosting decision tree and useless for linear model. So this example shows us that our approach to feature generation should rely on understanding of employed model. To summarize this video, as we do not train gradient an existing linear dependence, let's consider a next week example. First point will aid you greatly in upcoming advanced feature topics from our course. As in the first point, understanding of a model here can help us to create useful features. Let me show you an example. Say, we are to predict a number of apples a shop will sell each day in next week, and we already have a couple of months sales history as a training data. Let's consider that we have an obvious linear trend throughout the data, and we want to inform the model about it. To provide you a visual example, we put here the second table with last days from train and first days from test. One way to help model utilize linear trend is to add feature indicating the week number passed. With this feature, linear model can successfully find an existing linear dependency. On the other hand, a gradient boosting decision tree will use this feature to calculate something like mean target value for each week. Here, I calculated mean values manually and printing them in the data frame. We are going to predict number of apples for the 6th week. Note that we indeed have linear trend here. So let's plot how gradient boosting decision tree will split the week feature. As we do not train gradient boosting decision tree on the 6th week, it will not put splits between the 5th and the 6th weeks. Then, when we will predict number of apples for the 6th week, the model will end up using the value from the 5th week. As we can see, unfortunately, no usage of linear trend here. And vice versa, we can come up with an example of generated feature that will be beneficial for gradient boosting decision tree and useless for linear model. So this example shows us that our approach to feature generation should rely on understanding of employed model. To summarize this video, first, Feature pre-processing is a necessary instrument you have to use to adapt data to your model. Second, feature generation is a very powerful technique which can aid you significantly in competitions and sometimes provide you the required edge. And at last, both feature pre-processing and feature generation depend on model you are going to use. So these three topics in connection to feature types will be general theme of the next videos. We will thoroughly examine most frequent methods which you can be able to incorporate in your solutions. Good luck!
Stuck looking through dozens of lessons to find help on that one topic? Or do you have a test?
Hi there, this is Kevin from Data School. You're about to watch an excerpt from a private Q&A webcast that I hold every single month. This question is about how to select the best features for your machine learning model. Stick around to the end to find out how you can join these webcasts in the future. Thanks. So the first question I've got for today is from Davis Vickers, and he asks, hey Kevin, I discovered your YouTube channel as an aspiring data scientist. Your content has helped me so much. Question on sklearn. In logistic regression and other classifier algorithms, could you demonstrate a way to extract the best features with their coefficients and or score that is used in the model? I'm working with a logistic regression model that has over 400 features, and I'm trying to determine the best way to use a feature importance / selection. Okay, so that was a long question, but let me boil it down to this. Davis is asking how to perform feature selection. Okay, so he's got 400 features for his classification model, though the process would be roughly the same for a regression model. And he wants to reduce features. Now, why do you want to perform feature selection in the first place? The reason you do feature selection is because removing irrelevant features results in a better performing model, in a easier to understand model, and in a model that runs faster. So those are just three reasons that feature selection is useful. So I was trying to think of the best way to answer this question because unlike some questions, this one doesn't have a simple answer. And there are books about feature selection, I assume, but it's certainly a book-length topic. But I think the best way to answer this is 2 years ago, I was at PyData DC in Washington, D.C., and I attended a presentation called A Practical Guide to Dimensionality Reduction, and it was an awesome presentation. It's a great video, but what I'm going to do is I'm going to pull up his slides on screen, and I'm going to briefly go through a couple of his ideas for how you do feature selection, and then I'll talk very briefly about, how you do it from a practical level, not just kind of a high level. So it'll take me just a moment. I need to share one of my tabs, and let's do that. All right. You should see on screen the slides. So it's called A Practical Guide to Dimensionality Reduction, but it's about feature selection because dimensionality refers to the dimensions of your training data and number of rows and number of columns. So when we're talking about features, we're talking about columns. And when we're talking about dimensionality reduction, that means reducing the number of features. Okay. So let me go ahead and scroll down, and he has this big list of 12 techniques, that he uses for feature selection. And I'm just going to highlight a few of these and talk briefly about them. Okay. So the first one he talks about is based on percent missing values. So again, Davis has 400 features and he's asking, how do I remove some? And the first idea is to remove features that have a high percentage of missing values. Now, why is that useful? Because features that are mostly missing values are hard to learn from. A machine learning model learns from your data, and when most of the values are missing, it's hard to learn from. Now, that being said, that means reducing the number. It's about called A Practical Guide to Dimensionality Ideas for How You Do Feature Selection. And then I'll talk very briefly about, how you do it from a practical level, not just kind of a high level. So it'll take me just a moment. I need to share one of my tabs, and let's do that. All right. You should see on screen the slides. So it's called A Practical Guide to Dimensionality Reduction, but it's about feature selection because dimensionality refers to the dimensions of your training data and number of rows and number of columns. So when we're talking about features, we're talking about columns. And when we're talking about dimensionality reduction, that means reducing the number of features. Okay. So let me go ahead and scroll down, and he has this big list of 12 techniques, that he uses for feature selection. And I'm just going to highlight a few of these and talk briefly about them. Okay. So the first one he talks about is based on percent missing values. So again, Davis has 400 features and he's asking, how do I remove some? And the first idea is to remove features that have a high percentage of missing values. Now, why is that useful? Because features that are mostly missing values are hard to learn from. A machine learning model learns from your data, and when most of the values are missing, it's hard to learn from. Now, that being said, you can turn a missingness into a feature because, well, it might actually be a useful feature, a binary feature of like is missing or not. So even if you're dropping the feature itself, you might encode the missingness as a feature. Okay, so that's one idea. Next idea, amount of variation. So the basic idea is if a feature is mostly all the same value, then the model's not going to learn anything from it. So you should drop it. Okay. So that's the next one. Next idea is pairwise correlation. So if two of your features are highly correlated, you can drop one because they're redundant. So if you drop one, you won't actually be losing that much information in terms of what your model can learn from. Okay, so that's another idea. And as I'm going through this, you're probably thinking, which ones of these should I do? And I will answer that at the end. I will say that I'm going to provide a lot of ideas, but I'm not going to give you like, here's the one thing you need to do, because there is no one thing. If it was easy, everyone would do it the same way and everyone would just be like, here's what you do, and everyone would do it and it would work. But there is no one easy way. There's lots of ideas for how to do feature selection. The next one I was going to talk about is correlation with the target. So if a variable, aka feature, has a very low correlation with the target, then you can probably drop it. Now, this might, like any of these techniques, can miss a useful feature because there might be a feature interaction such that, you know, variable A does not correlate with the target, variable B does not correlate with the target, but variables A and B together, if you turn them into a combined feature, then they are. But there's only so much you can do. You can't, generally speaking, try every possible combination of features and especially when you have 400 features. So you have to use some sort of technique to do this. Okay. Number 8, 9, and 10 is talk about forward, backward, and stepwise selection. And the way forward selection works, and then I'll talk about the other two, is you start with one feature that you believe to be the best feature and you evaluate. I mean, you could actually write a loop even, just try one feature in your model, loop through all 400, and do cross-validation with the relevant evaluation metric and figure out, okay, here is my one best feature. And you add that to your model. Then you try adding a second feature. Which do you add? Well, the best one as determined by some criteria. So you keep doing that until some threshold is met, either a certain number of features you define, some performance metric, et cetera, et cetera. Backward selection is essentially the reverse. You start with all of them, you subtract one, you subtract the least important one, and you keep subtracting and subtracting again until you meet some sort of stopping criteria. And then stepwise is kind of a combination of the two. Okay. I'll just have a couple more, and then I'll kind of summarize what I've talked about here and provide some other tips. So 2 more. In his recommendations, Lasso. Lasso is actually an algorithm for creating a regularized linear model. Okay. You may have heard of lasso regression and ridge regression. They're 2 types of regularized regression. Well, a nice property of Lasso is you change this regularization parameter with Lasso, and like when either the value is really large or really small, I don't remember, there's no regularization and you just have a plain linear model. Then if you increase or decrease that regularization parameter slightly, then it does regularization, which with Lasso actually drops coefficients all the way to 0, and a coefficient of 0 means the feature has been dropped. So it essentially does feature selection for you. Now, I just said Lasso is for a regularized linear model. A Lasso is for regression, but there's regularized logistic regression, for example, that can work the same way. I think I've said enough about that. The final idea in this presentation is tree-based models. And you may know that with ensembles of trees, of decision trees, such as random forests and other similar models, it automatically computes something called feature importances. You could set a threshold and say, if my model says a given feature's importance is below a certain threshold, then remove it from the model. So that's another idea. These last 2 ideas are only useful if that is your model that you're using, or you could theoretically use a tree-based model to look at feature importance and then not actually use a tree-based model for your model that you're building. Okay, so I know that was a lot of ideas thrown at you quickly. I'll just wrap up with some advice and then talk about how to implement this. In terms of implementation, scikit-learn does support some of these. Just search for scikit-learn feature selection, or I'll have a link in the webcast notes, and they have a page in the user guide about feature selection techniques they support, and many of these are included in some form or fashion. The most kind of sexy one is forward and backward selection, because it feels like it's doing a ton of work for you. And it is. That's not currently available in scikit-learn. It is available in a package called ML Extend, and I will link to that in the webcast notes. Though that actually might get merged into scikit-learn at some point. I think someone is working on that right now. I saw that on the scikit-learn mailing list. So what is my general advice? I've given a lot of ideas. My general advice is to try simple techniques, because the more complicated you get, the easier it is to sink a bunch of time into it and to make a mistake. My next piece of advice is always check if what you're doing is actually helping or hurting. So don't assume that any given technique is useful. You need to set up your model evaluation procedure first, and then try these things and see if they are actually helping, because if they are not, then abandon them. And you're never going to know a priori whether something's going to work on a given data set or a given problem, so you have to try it. And final piece of advice is to generally, I say focus on things built into scikit-learn, because when you're writing custom code, it's easy to make a mistake and it's a lot of work. Scikit-learn code is good. Even like ML Extend, it's good code. I respect the person who wrote the package, but that's not his focus. And so over time, it will probably get out of date. And if there are bugs, they probably won't get fixed because you don't have a bunch of contributors focused on it like you do with scikit-learn. So do simple things, check whether it's working, and generally stick to things available in scikit-learn because it will make your life easier and you're less prone to make mistakes. Hope this video was helpful to you. If you'd like to join my monthly webcasts and ask your own question, sign up for my membership program at the $5 level by going to patreon.com/dataschool. There's a link in the description below, or you can click the box